Bismillahirrahmanirrahim. Assalamualaikum and good day for everyone. Today we are going to present to you about our group assignment project for subject Fluid Mechanics 2, BMCG 3613. So before that, we are going to introduce to you about our group project member. First of all, let me introduce myself as a group leader. I am Ahmad Arif bin Zainar, B0421102000. Secondly, Amirul Afzan bin Azmi, B0421111024. Number 3 is Damian Nurkalisa binti Jamaluddin, B0421110125. Number 4, Emmanuel Pilai Vela Singham, B0421110189. Number 5, Goh Ziu Lee, B04210221. And lastly, our member in the group is Ainsa binti Saidi, B0420100257. So this is our group. So after people know about our group, so let me tell you about the task allocation. The task allocation is the thing that distributes the task so everyone can do the work. So what work they will do? So first of all, the introduction to our topic is presented by Damia. Theory related to our topic is Damia and Go. Explain the problem that need to be solved in the simulation. We'll explain by Emmanuel and Damia. Geometry details and dimensions will be explained by Mai and Arif. Explain every step of method simulation as inlet, outlet and boundary meshing, explained by Mai and Arif. The result will be explained by Ainsa and Go. Related result will be explained by Damia and Emmanuel.
Assalamualaikum warahmatullahi wabarakatuh. My name is Damian Nurkalisa binti Jamaluddin. My metric number is B0421101125. Pipe flow simulation. So what is pipe flow simulation? It is a type of computational fluid dynamics known as a flow simulation, which digitally reproduce flows in surface water or collection system. By using flow simulation, it is possible to forecast and examine how complicated geometry might affect a flow in a real-world setting. Furthermore, pipe flow simulation can determine problems, establish solution and procedure, and forecast the impact of system modification. In fluid mechanics, pipe flow is a type of liquid flow within a closed conduit, such as a pipe or tube. There are three fluid flow, which is laminar, turbulent, and transition region. So in this project, we will use CFD software to run an analysis of the flow inside a pipe with different inlet diameter. Next, for this pipe flow simulation, it is related with the Bernoulli equations, where we want to measure the pressure and magnitude velocity. According to the Bernoulli equation, the fluid velocity changed when an incompressible fluid passes through pipes of various size. The system accelerates as a result of this change, which change the stress and pressure acting on the pipe's cross-sectional area. We can calculate flow rate using the Bernoulli equations, which is pressure, kinetic energy, and potential energy of the first pipe is equal with the second pressure, kinetic energy, and potential energy of the second pipe.
Hello, my name is Emmanuel and I'll be explaining about the problem that needs to be solved in the simulation. So basically the problem that is solved by using the simulation is we can figure out how the thickness of pipe affects the velocity of the fluid flow inside the pipe, and by finding this we can also determine the static pressure in various regions of the pipe.
Assalamualaikum dan selamat sejahtera. Nama saya Amirul Afzan bin Azmi. Nombor metrik B04211024. Saya akan menerangkan tentang geometry detail and dimension. Untuk projek kami, model untuk projek kami mereka satu pipe berbentuk U, di mana di tengah-tengah pipe itu ada reduced pipe ataupun pipe yang mengecil, kerana kami ada dua saiz yang berbeza untuk outlet dan inlet. Untuk outlet kami menetapkan diameternya adalah 70 mm diameter, dan untuk outlet kami menetapkan 43 mm diameter. Dan untuk kelebaran model ni kami menetapkan 700 mm, dan untuk kepanjangannya kami menetapkan 1250 mm. Dan untuk ketebalan dinding model ini ataupun wall thickness kami menetapkan 3 mm. Okey, itu saja daripada saya. Sekian, terima kasih.
Hello. So this is the method of simulation. We are using this method of simulation for fluid pipe flow using CFD. another two flow pipe. It consists inlet and outlet. So after that, we are heading towards building surface, where we need to do this for void fill. So we are building surface on outlet first, like this. And we are building surface at the inlet, like this. So we are building the surface specifically for void fill. So after that, we need to change the material of our pipe. So we need to consider the material of our pipe. So we have to choose the material of our pipe what we want to select. So we decide to select a stainless steel. So our pipe will make up for stainless steel. Like that. And then secondly, for the second part, we have to consider the fluid running through our stainless steel, which we consider as a water. So stainless steel and water is our fluid and our material. Then proceed towards the boundary condition, where we need to decide the flow of the water. So in inlet, we set the flow for the velocity we select is 10 meter per second. So the flow with velocity of the pipe, the flow of 10 meter per second, and then we are selecting the outlet because we want to know the velocity, the exactly pressure and velocity in the outlet. And then we start to the mesh. For mesh, don't worry because it is automatically mesh, so we don't worry too much about meshing size because it is automatic. And then after we finish up all those things, then here we go, we have to solve the problem. So this is our solve, and the result will come out for a second. So this is our result. So after we solve our pipe, then the result will come out. So at the bottom of the picture, so there is a result. There is an iteration plot. So at the right, we will see the Vx velocity, Vy velocity, Vz velocity, pressure, temperature, TKE, TED, and scalar. So all these are legend. Then at the up and the left of the picture, we see the velocity magnitude. The higher the number, the higher the magnitude of velocity. So how we are going to see that? So we are going to see that by using traces. So as you can see, I click water, click stainless steel, and this is our material. This is our mechanism, the flow, which is water. So we click traces and we click add. Traces and we click add. Then we have to make dot at the hole of our pipe. So we're making dot at the hole of our pipe to show where the traces, to show the flow, to show to everybody the velocity magnitude of the water once the water getting inside the pipe. So this is our traces. So we are setting at the surface of our hole. Then we set it inside our pipe. So you can see the hole on the surface of our pipe. Then yeah, this is our result. So this result shows the higher velocity at our pipe is at the inlet of our pipe. So the velocity will become higher once the pipe velocity getting smaller. So the velocity will become higher once the pipe diameter is smaller.
This is the convergence graph for our pipe flow simulation. When a simulation is started, the force oscillates quite a lot because the velocity pattern has not yet been modified or tweaked around the shape. So, it needs to find a stable state, and that's what you see here. The convergence plot shows the change of various variables as the solver runs through many iterations of solutions. When this line stops changing, or the slopes become zero, the solution is said to have converged for a steady state flow. We have run the simulation to 35 iterations. As we can see here, there are different color lines. The dark blue line indicates the velocity at the x direction. The light green one indicates the velocity at the y direction. And the pink one indicates the velocity at the z direction. The black line represents the pressure in the pipe. We can see that the graph increases before it converges to a steady state flow. This is because when a fluid passes through a pipe, a reduction in the diameter of the pipe can compress the fluid. It flows faster, which increases the flow rate. Next, we can see the light blue line indicating the turbulent kinetic energy, or TKE in short form. Generally, TKE is defined to be half sum of the variances of the velocity components. TKE measures the intensity of turbulence in a flow and help in identifying the stability of the flow. The dark green line represents the turbulent energy dissipation. TED is determined by viscous forces affecting the body of the fluid, leading to a breakdown of eddies until eventually eddies diminish in size and are unnoticeable. That's all from me. Next, my group member Go will explain about the traces in our pipe flow simulation.
Okay, thank you, Aisa. I will continue the presentation. Okay. Once you reach that link between smaller diameter pipe and larger diameter pipe, you can see how the velocity magnitude change. The smaller of diameter pipe is, the faster the fluid flows. Based on the Bernoulli principle, states that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure or fluid's potential energy, which was shown in the diagram. You can see after this interlink, the velocity has gone up to maximum. You can see the traces are red, which indicates the high speed of velocity magnitude, and green indicates medium speed of velocity magnitude. So this is one way of interpreting the result. Thank you.
Okay, next, the correlation between result and the theory. As we can see through our result, the velocity magnitude at the smaller outlet diameter is higher than velocity at the inlet diameter. It is because the velocity is increased at smaller diameter pipe, and the increase in velocity occurs simultaneously with a decrease in pressure or change in the fluid gravitational potential energy. So that we can see that the pressure is decreased when passing through a small diameter pipe. This is also because according to Bernoulli equation, higher pressure regions have lower fluid speed and lower pressure regions have higher fluid speed.